So in the previous two lectures, we studied some model physical systems where the concept of quantum field arises more or less naturally. Now, the main interest of our course will be field theories that describe fundamental interactions between elementary particles. And so they should be consistent with basic principles of physics that we know, in particular with relativistic invariance. So we will study relativistic field theories. And the first type of relativistic fields that we'll study is the Klein-Gordon field. So, since these fields are relativistic, the natural habitat for them will be the Minkowski space. With the 4 coordinates as usual. So we unify spatial coordinates and time in one 4 vector, x mu. And our fields will be functions of x mu. So fields will be functions of x mu, and well, they themselves should transform nicely under Lorentz transformations. And the objects that do so are tensors in general. So these fields will be tensors with some number of indices. So the fields should transform covariantly under Lorentz transformations. So the simplest example is the field that doesn't transform at all, so the scalar. And the Klein-Gordon field is the scalar field. So first we will study fields that do not transform under Lorentz transformations. So I remind you that important notion in relativity is the interval between two events. So here I will always sum over repeated indices. This is the usual Einstein convention. And the metric tensor is diagonal, and we will take it in the signature where the spatial coordinates have negative signs. I don't know what was the convention in the relativity course. Perhaps it was opposite. That's it's always the case. So people doing relativity always use the minus plus 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 convention, and in the field theory, they use plus minus minus minus. Just the fact of history. So we will stick to this convention. So this means that the interval between two events that happened in the same point coincides with the time interval. Then on the light cone it is 0, and is negative for space-like separated events. Okay, so then tensors and vectors have a certain number of Lorentz indices, and we will use this metric to contract the indices. So for instance, if we have 4 vectors v and u, v scalar product with u is defined as g mu nu, v mu u nu, and this is the same as v mu u mu. So we'll use all these standard conventions of special relativity. All right. Another remark is about units. So we will be interested in the regime where both relativistic effects are important and quantum mechanics will be also important. So both C and H bar will be, in a sense, finite. So you can think of non-relativistic approximation as an expansion in 1 over C. The same as in quantum theory, you can think of semi-classical expansion as an expansion in H bar. So it's therefore useful to keep them as parameters. But in our case, the velocities will be comparable to the speed of light or equal to the speed of light. Quantum mechanics will be important. So we can choose units such that the speed of light is equal to 1 and H bar is equal to 1. So this simply means that we define velocities as, so if we say that velocity is equal to 1/2, then this means that the velocity is just 0.5 times c. Okay, so we measure velocities in units of the speed of light. So velocity becomes dimensionless. Therefore, the units of time and units of distance are the same. The units of energy is the same as the units of mass, are the same as units of mass because of E equals mc squared relationship. So this is also the same as units of momentum. And also, now what happens when we put H bar to 1? Well, H bar is the right-hand side of the uncertainty principle. So P times X now is dimensionless. So distances and therefore time intervals are measured in units inverse to those of momentum and to those of mass and energies. So there is just one unit, one basic unit, which we choose to be the unit of energy. So we will stick to energy units. And as a basic unit, we will use electron volt. So this is a common unit. It comes from particle physics, and it's the energy that an electron would acquire by passing a potential difference of 1 volt, by definition. So well, to give you an idea of what it, of how much it is in other units, then say in temperature units, electron volt is roughly 10 to the 4 Kelvin divided by Boltzmann constant. Then we can express masses of particles in electron volts. So for instance, mass of the electron will be 0.5110 mega electron volts. Then proton mass is 2,000 times larger, so it's 938.3 MeV, and so on. So we can in principle express anything we want in electron volts, like centimeters would be inverse electron volts. One can express 1 centimeter in these units. So we will not write, we will not, instead of h bar and c, we will write always y in all the formulas. Okay, so with these preliminaries, let me now continue to describe the theory of the Klein-Gordon field. So the Klein-Gordon field, what is it? It is a scalar function of coordinates, so of space coordinates and time. So this will be a Klein-Gordon field. Scalar field. And we need to write down some equation that is satisfied. So like Maxwell equation for electric and magnetic fields. So this should be a second order differential equation. And actually there is no much choice. So the only equation that we can write is this one. And this is called Klein-Gordon equation. So what is the rationale behind? So first of all, this is the only relativistically invariant equation of the second order acting on the scalar field, with the scalar field. So, which is linear. So really, if we start with the operator that acting on the field should be second order derivative. So the second order term, well, it contains two derivatives, and there is only one way to contract their indices, which is with the g mu, right? So we get d squared. The linear term must be absent because one derivative has an index, and we have no other vector to contract it with. And well, we can add some constant m. So this is actually the only Lorentz invariant second order differential equation that we can write. So the second rationale comes from, we can start from the form momentum of a massive particle. So you know that the form momentum includes energy as the time-like component and then the usual momentum as its space component. And for a relativistic particle of mass m, the energy should be equal to square root of p squared plus m squared. This is the famous Einstein's relationship. So here written without the factors of c. So it should be c to the 4 and c squared here. But we set c to 1. And then this can be written as an equation for the 4 vector that the scalar square of the 4 vector of the momentum 4 vector should be equal to m squared. So and then, as usual in quantum mechanics, we replace p mu by I times d mu where by dmu we denote the derivatives with respect to x. Then we substitute this into the equation p squared minus m squared plus 0, and then we get the Klein coordinate. Okay. So p squared minus m squared then becomes minus p squared minus m squared. So this equation, in a sense, is a way to represent the dispersion relation for a massive particle. And so the physical meaning of the parameter m is just a mass. So it should somehow describe particles of mass m upon quantization. So this is what we could expect. Now the way we will proceed here is a little bit different from what we have done on the previous two lectures. So there we started with some physical picture of, I don't know, atoms vibrating near their equilibrium positions, and then derived what the Hamiltonian looked like in the convenient variables. So here we will do sort of an opposite thing. So we start with this equation, which has a priori no physical motivation, and then we will proceed through so we'll regard this as a dynamical system where phi is a dynamical variable, and then quantize it as textbooks in quantum mechanics prescribe. So to quantize, we need to write this equation in the Hamiltonian form. So we need to understand what are the canonical variables. And so this can be done by first deriving from the action. So indeed, there is an action principle behind this equation. So one can see that if you start with the action of this form, then Klein coordinate equation arises as the arises from the condition that the variation of this action vanishes. Indeed, let's take delta S. This will be equal to d for x d mu delta phi d mu phi minus m squared delta phi phi. In the first term, we integrate by parts. And then we get here minus d squared acting on phi minus m squared phi. So you see that delta S equals to 0 is equivalent to the Klein coordinate equation. So once we have the action, we can write down the Lagrangian, and from the Lagrangian we can derive the Hamiltonian, and then proceed with quantization. Yes?
Sorry, if I can ask a dumb question, is phi here complex valued or real valued?
This is real valued. We will also consider complex valued fields later. So here it is a real variable. Yes?
So I was wondering how you just theoretically get that expression.
This one? Well, it's again, you can guess that it should be like that because this is the only Lorentz invariant expression that contains two derivatives and the scalar field that you can write. So if you require this to be Lorentz invariant, then this is the only possible expression that you can write, and then you can check that it leads to the Gordon equation. So, well, the action in classical mechanics, the action is written as an integral of the Lagrangian So here you see that we have four-dimensional integrals. So indeed we can separate time integration, and then the Lagrangian will be whatever remains of that, where this curly L is 1/2 phi minus 1/2 of m squared phi squared. So naturally, this curly L is the density of is Lagrangian density. Since our field is distributed in space, the Lagrangian is an integral over some density over the whole space. Okay, so, and then we want, from the Lagrangian formalism, we can always pass to the Hamiltonian formalism. And there there is some unpleasant feature of that, because the Hamiltonian formalism requires us to separate time from space coordinates. So we need to consider evolution in time, and the time variable is somehow special. Whereas in relativity, we are allowed to do transformations between space and time coordinates. Okay, so the Hamiltonian formalism is not manifestly Lorentz invariant. So at some point, we need to give up manifest Lorentz invariance to be able to quantize the field. So we'll fix this in a moment, by the end of this lecture, I suppose. But just to proceed along the standard, textbook procedure, we will need to give up Lorentz covariance for a moment. So then we should separate space and time derivatives. So we write the Lagrangian as 1/2 of phi dot squared. Dot denotes time derivative minus 1/2 spatial gradient phi squared, and then the term with mass squared. Okay, so this three terms have clear physical meaning. So this is the kinetic energy of the field. It's like q dot squared term in the mechanics of, say, single particle. And these two terms correspond to the potential energy. So the Lagrangian indeed has the usual form of kinetic energy minus the potential energy. But here you see that potential energy comes in two forms. So there is a energy that's grows when the amplitude of the field is big. And this term is big when the gradients, spatial gradients of the field are big. So both cost energy. So we cannot make, so if you make the field big, then it will have big energy. Or if it varies in space rather fast, then it also will cost a lot of potential energy. Okay, so then how should we view this from the mathematical perspective? Well, we should think of time coordinate, time as time, but then the spatial coordinates, they just label degrees of freedom at each point. So, the spatial coordinates, from that perspective, they're not really coordinates, they're just labels that are similar to an index, say, on the canonical variable in classical mechanics. So, well, if we have in classical mechanics, we would have some coordinates q, I of t, and here we have phi of t and x, and in principle, we can write this as phi x of t, writing x as an index. So from Hamiltonian formalism perspective, this is just a label that enumerates various degrees of freedom. Well, since we are dealing with field theory, this label is continuous and not discrete, but that really doesn't matter. So what it means is that we should take variational derivatives instead of usual derivatives. Apart from that, there are not so much differences. So in particular, we can define a conjugate momentum to the field, which is the variational derivative of the Lagrangian with respect to the velocity. Which is simply the velocity of the field. And then Hamiltonian is given by P dot Q minus P dot Q dot minus the Lagrangian. So the dot is contains summation over all indices in usual mechanics with finite number degrees of freedom. Here, the summation is replaced by integration. So in the Lagrangian, we should replace the velocities by express them in terms of momenta. And then what we get is the Hamiltonian. And so then we know how to proceed. We just declare that pi and phi are canonically conjugate variables that satisfy the canonical commutation relations. And then we need to diagonalize the Hamiltonian to find the spectrum. In fact, we have already done this because this Hamiltonian has precisely the same form as that for phonons, except that we didn't have this term. And for phonons, we also had, so this term was multiplied by the speed of sound squared. So here it is multiplied by the speed of light squared, but we set it to 1. Okay, and this is just because in the Klein-Gordon operator, d squared is just the wave operator. It's d time squared minus d space squared. And so what we are doing is we are quantizing the wave equation, but with an extra term related to the mass of the particles. So the quantization will proceed through the same steps, and it's just the formulas will be absolutely the same. So we actually solved this problem already. But now the system enjoys an extra symmetry, which is relativistic invariance. And so we want to see it in the final answer. And actually also in some intermediate steps. And this way of doing things, that is not particularly illuminating in this respect. So in particular, one property that we want to, should be certainly true, is that the Hamiltonian should be, the energy should be conserved, right? So the Hamiltonian should not depend on time. So this is, of course, possible to check. One has to just differentiate, use the Klein-Gordon equations, and then, well, the result should be 0. Now, if you do it explicitly, that's not really a simple exercise. It takes a few lines of calculation. And this is because in here we have broken Lorentz invariant. So this expression is not manifestly Lorentz invariant. And so we need to break it in the Klein-Gordon equation, separate time derivatives from spatial derivatives. It's a bit of a mess. So it's just technically not very simple. So this is really not satisfactory that we cannot immediately check the basic principles like energy conservation just because they are written in a way that's not Lorentz invariant. So our next goal will be to understand how to write conservation of energy in a Lorentz invariant form. And in general, how to write in Lorentz invariant form conservation of anything. So I'll make a sort of side remark on conservation laws. So suppose that we have some quantity, some conserved charge that doesn't disappear. Then what does it mean? So suppose we take some finite volume of space. So now I'm again in this 3+1 dimensional picture. Well, we don't have well, we separate space and time. So we have some volume V that's surrounded by a surface S. And we want to write down the conservation of some quantity, like, I don't know, that mathematically write down the, describe the fact that the number of people in this room is conserved. Right? So, and it can change, of course, because people can come and go outside of the room. So the change, the total number of people in the room is therefore equal to the difference between influx and outflux through the doors, right? So mathematically, we can write that this as an equation that the time variation of the total charge inside this volume that we can write as an integral of the local density of this charge is equal to the influx through the boundary. So we can integrate, we can consider influx through some small patch of the boundary. So locally there is some flux vector J, and we need to project it into the unit normal to surface S at that point, and this would be the local influx of charge outside of this volume. So the total influx will be the surface integral of the local influx, which is the projection of the flux onto the unit normal to the surface. So now, using the Stokes theorem, this can be written as a volume integral. So by the Stokes theorem, the second term is equal to the volume integral of the divergence of the flux. But now it's clear that, okay, so this equation was derived without any reference to what this volume was. We could have taken it arbitrary, which means that the only way this to be zero is that the integrand is zero. So the conservation law then can be written in completely local form. Is an equation, first order differential equation that relates the time derivative of density and with the divergence of the flux. So this is a universal equation. Its conservation of anything can be written this way. Now the question is if this equation Lorentz invariant or not. Now in a way that we derived it, it's wasn't clear because we didn't assume anything about Lorentz invariance. But on the other hand, it better be Lorentz invariant because, okay, it's a general equation, and it would be very bad if conservation of some quantity would violate Lorentz invariance. So to see that this equation doesn't violate Lorentz invariance, well, one can really see that this doesn't happen. That this equation actually is Lorentz invariant always, and this is because we can combine the density and the flux into a single four-dimensional vector. Whereupon the conservation law becomes an equation for the four divergence of this four vector, which should be zero. So whenever we have a conservation law, we then are able to construct the current four vector. So this is called the current four vector. And this current four vector will have zero divergence. And vice versa, once we have, so if we have some dynamical system, like some sort of field theory, and then we can build a four vector that has zero divergence, then we have a conservation law. Yes?
For the conservation law, should mu four vector decline with the minus?
So not in these conventions, because you see this is upper index and this is and this is the lower index. So
is it plus minus minus minus? So if you want to recover the conservation law, first time.
well, let me write this in components. So this will be equal to d0, j0 plus d1 J1 plus D2 J2 plus D3 J3 equals to 0. So the plus here is just because the indices already stand in the right position. So if this were, yeah, we can, right, so we can lower the index on J, and then this will be on the minus.
Yeah.
So anyway, so this is the relativistic invariant form of the conservation laws. But of course, one may wonder who prescribed this to be a for vector, because if you write some quantity in this way, we sort of assume that rho and J transform to each other under Lorentz transformations. So that this is not just a way of. So I mean that we assume something more than just rewriting this equation. We assume that Lorentz transformations, when act on the coordinates, they should also act on rho and J in such a way that they mix their components in the correct way. So let us check this. So, well, what is rho? Well, if we say take a small infinitesimal volume inside the fluid that contains, so that the charge in sitting in this volume is delta Q, then rho is just the ratio of delta Q over delta V. Now, so how does this transform under Lorentz transformations? Well, it's not immediately clear, because if you go into some other reference frame, delta Q shouldn't change. Delta Q is just, if delta V is this room and delta Q is the number of people here, someone running very fast will still see the same number of people, right? So delta Q is the same. But delta V actually will change because of the Lorentz contraction. But here it stands in the denominator, so it's not very easy to understand how rho transforms. What we can do is we can multiply and divide it by delta T. And we know that the 4 volume is invariant. Now, what is J? Well, J is, again, it's proportional to the density times the velocity, local velocity of the fluid. So local velocity can be understood as the distance delta x. So suppose that this, we are considering some fluid that flows in space. And so we just monitor one little volume in this fluid. So if the fluid moves, then this volume will, it will also move with the fluid. And in time delta t, it will shift by distance delta x. So the velocity, of course, is just delta x divided by delta t. And then here we immediately see that there is some invariant quantity delta Q divided by the 4 volume times delta X. And so indeed delta T and delta X transform as a 4 vector. So rho and J have the right transformation laws. Rho J therefore transform as delta T delta X. And delta T delta X transforms as a vector with upper indices. So our conclusion that we should combine rho and J into a 4 vector was correct. Okay, so to conclude, the conservation laws can always be written like that. And the next goal will be to understand, looking at the field equations or at the action, how can we see what conservation laws will be present in the system. So let us make a break for like 3 minutes.